Well, hello there, everybody. It's time for another chemistry review. Yeah. Now we're on to Unit 4, which is all about the nucleus of the atom. In this topic, 4.01, we're going to take a look at the particles that make up the nucleus, which are called nucleons. There we go. So, why can't you trust atoms? They make up everything. Ugh. So, what exactly does an atom look like? Well, the truth of the matter is we really don't know. And it's possible we never will know because the more we find out about these particles, the stranger they become, the more ephemeral and ethereal they become. But we can do it in a more simplified manner. And that's what we're going to do today. In the 1830s, John Dalton suspected that atoms were spherical in shape and that all atoms of the same element have the same atomic mass. Now, he got that last part right, and I guess on the whole, if you describe the shape of the electron cloud around the nucleus, yes, okay, spherical seems to be pretty much on the money, but he's talking about a solid, indestructible sphere, and we know that's not true anymore. In 1897, J.J. Thomson discovered that electrons had a negative charge, came from an atom, and therefore his idea was the atom was a positive sphere embedded with negatively charged electrons. And he got the electrons part right, and the fact that the rest of the atom overall has a positive charge, but even this was too simplified. Then in 1911, we had Ernest Rutherford, who did the gold foil experiment. And he discovered the nucleus of the atom, which was positively charged, and electrons orbit around outside. The manner of the orbiting was unknown, but the picture that most people had in their heads were that electrons would orbit the nucleus in much the same way that planets orbit around the sun. We now know that that's not true either. The truth is much weirder. In 1914, the nuclear idea still remained, but Niels Bohr interpreted spectroscopic data to discover the concept of electron energy levels, which he called shells. And when electrons fall from a higher shell to a lower shell, they always emit the same frequency of light. And the frequency corresponds to an energy, and the energy corresponds to the shell. This is, in a very simplified way, pretty close to the money. And then we got the quantum mechanical model, which just does a much better job of getting a more granular look at what's happening with the electrons. The electrons don't occupy any specific orbit. However, they are statistically likely to exist for the most part, within regular geometric volumes of space surrounding the nucleus. These are called orbitals. And this is about as close as we've gotten to a picture of what the atom actually looks like. It's a little strange, and if you ever had to do the math, let's just say that the Schrodinger equation is a whole lot of fun. But anyway, we've actually been able to image not atoms exactly, but the effect of the repelling force of the electrons that are on the outside of an atom. So what happens is you basically scan the surface with um, a needle, and what the needle does is it detects the repelling force between the tip of the needle and the atom that it happens to be passing over. And if you take a look at the image on the right, the bright purple area would represent the area with the greatest repelling force. And the areas that are in the red and orange would indicate the lowest repelling force. So the repelling force, at the very least, the field surrounding an atom, is spherical in shape. So Dalton at least got that part of it right. And it's an interesting discovery. These are imaged atoms. And then again, it's not actually an image. An image would require you to reflect light off of a surface and then capture it. Again, all we're doing is we're recording the force of repulsion between the tip of a scanning needle and the electrons in the outer parts of these silicon atoms. Sometimes it's also called an atomic force microscope. Now, what about the middle of the atom, the nucleons? Well, the nucleons, the particles in the nucleus, are the protons and the neutrons. And these, in turn, are made of particles called quarks. But we're not going to get that deep into it. We're just going to look at the fundamental particles. Well, they're not really fundamental. That would be the quarks. But the particles that give atoms their characteristics, the protons and the neutrons. Here indicated the protons and the neutrons just as red and blue spheres, but again, this is a major oversimplification. We don't actually know what a nucleus looks like. We do know this about protons, though, that they have a charge, a unit charge of +1, which is 1.6 times 10 to the negative 19th coulombs, if that interests you. And this charge of +1, this fundamental charge, is per proton. So if you had 5 protons, for example, then the charge would be +5. Each proton has a mass of 1 atomic mass unit, which is 1.6 times 10 to the negative 24th grams. Interestingly enough, if you multiply this number by Avogadro's number, 6.02 times 10 to the 23rd, you get 1. So Avogadro's number is the number of atomic mass units you need in order for you to have 1 gram worth of mass. The atomic number is just the number of protons in the nucleus, and it is the number that identifies an element as being of a particular element. So if you have an atomic number of 8, for example, you have 8 protons in the nucleus, only atoms of oxygen have 8 protons in them. If you were to suddenly remove a proton and only have 7, then you're looking at an atom of nitrogen. So the atomic number is unique to every element, and every atom of that element will always have the same number of protons. The nuclear charge is positive because protons are the only positively charged particle in the nucleus. So once again, if there are 5 protons in the nucleus, the charge of that nucleus will be +5. And that is important in understanding how electrons will be attracted to the nucleus and how it relates to atomic radius as you go across a period on the periodic table. But we're going to look at that in more detail when we look at the periodic table and bonding unit. And it will also be important in understanding the concept of electronegativity. So carbon, all carbon atoms have 6 protons, and all iron atoms have 26 protons, and all oxygen atoms have 8 protons, and all aluminum atoms have 13 protons. So every element has its own unique number of protons. As an interesting aside, if you look at the electron configuration underneath the atomic number, if you were to add up those electrons, they equal the atomic number. For example, carbon 2-4, that would be 6 electrons. 2 plus 8 plus 14 plus 2, well, that's 26. 2 plus 6 is 8. 2 plus 8 plus 3 is 13. So the number of electrons is always equal to the number of protons in a neutral atom. Lead has 82 protons and electrons. Now, the other particle is the neutron, and neutrons, well, they're neutral, right? You know the old joke. A neutron walks into a bar, asks the bartender for a drink. Bartender produces a drink for the neutron. I'm not exactly sure what a neutron would drink, but anyway, after finishing up, the neutron says, "Hey, barkeep, what do I owe you?" And the bartender says, "For you, neutron, no charge." You can't even give a Visa or a MasterCard to a neutron because they have no charge. All right? So, yes, terrible jokes. Chemistry jokes are, by their very nature, horrible. Okay. Each neutron also weighs the same as a proton. Well, at least when you take it to the nearest whole number atomic mass unit. Neutrons are actually infinitesimally larger in mass than a proton. But for the purposes of what we're doing here, we're going to just go to the nearest whole number. Each neutron has a mass of 1 atomic mass unit, which means that the nucleus, which contains pretty much all of the mass of an atom, will determine the mass number of the atom. The mass number is simply the number of protons plus the number of neutrons. See, because 5 protons will weigh 5 atomic mass units, and 6 neutrons will weigh 6 atomic mass units. So if your nucleus has 5 protons and 6 neutrons, the mass number of your nucleus will be 11 atomic mass units. The only other particle that an atom has are electrons, and its mass is not significant enough to affect this mass number, at least not at the whole number level. The number of neutrons, therefore, would be the mass number minus the atomic number. So if you have a mass number of 11, that means there are 11 particles in the nucleus. If 5 of them are protons, the remaining 6 are the neutrons. Now, the atomic mass that's given on the periodic table is a weighted average mass. We're going to explain that a little bit further down the road, but let's just, for the sake of fun, let's just round these to the nearest whole number to start with. If the atomic mass is 12, that means there are 12 particles in the nucleus. The atomic number is 6, which means that 6 of those 12 are protons. The remaining 6, therefore, would be the neutrons. Iron has, if we round it to the nearest whole number, has a mass number of 56. That means there are 56 particles in the nucleus, 26 of which are protons. So if we take the difference, we'll have 30 neutrons. And you can do this with any element. Oxygen has a mass of 16, which means there are 16 nucleons. 8 of them are protons, and therefore the remaining 8 will be neutrons. Aluminum has 27 particles in its nucleus. 13 of them are protons, which means the remaining 14 will be neutrons. And then you can do the math yourself, because I'm just too lazy to do it. It would be 207 minus 82. Okay, so with that in mind, why is this a weighted average mass? Well, you see, you must have the same number of protons in order for the element to be the same. But you don't have to have the same number of neutrons. There are actually several different kinds of atoms of carbon. Some carbon atoms have a mass of 12, some have a mass of 13, some have a mass of 14, and there are even more additional flavors of carbon than this. And the only difference between them is the number of neutrons. And because we can have multiple flavors of carbon, we actually come up with a name for it. It's not called flavors, it's called isotopes. And these are atoms of the same element that differ in their number of neutrons, and therefore they differ in their mass number. Now, here are 3 isotopes of hydrogen. We have protium, which has 1 proton, deuterium, which has a proton and a neutron, and tritium, which has a proton and 2 neutrons. Notice that they all have only 1 proton. That's what makes them hydrogen. But the number of neutrons can be different. Now, protium is by far the most common of all of the isotopes. Deuterium is the second most common, and tritium, which is radioactive, is actually pretty rare. But they are all atoms of hydrogen. The only difference is that they have a different number of neutrons, and therefore their masses are different. Protium has a mass of 1, deuterium has a mass of 2, and tritium has a mass of 3. The periodic table gives you the weighted average mass of all the possible isotopes that are naturally occurring for each element. These would not include any isotopes that we created in a lab using a particle accelerator, which we'll discuss later in the unit. So as you can see, the weighted average mass of hydrogen is just slightly more than 1. This tells us that, like with any average, the number the average is closest to, protium must have the greatest abundance in nature for the average to be closest to its mass. There are multiple isotopes of carbon. Now, if you look on the periodic table, the atomic number for carbon is 6. So you have carbon 12, which can be represented as C-12, the 12 meaning the mass number, or you can put the mass number in the upper right. No, that's not right. I can't tell my left from my right. Oh, it's so frustrating. The upper left corner of the element symbol, 12C. Now, if you count the number of protons and neutrons. The protons are the red ones. There's 6 protons. Well, all carbon atoms must have 6 protons. Count up the black circles and you'll come up with 6 neutrons. So this gives you 12 particles in the nucleus for a total mass of 12. 6 protons, 6 neutrons. Now, any other isotope of carbon will also have to have 6 protons, but the number of neutrons will vary. So carbon 13, well, carbon 13 has 13 particles in the nucleus. You see, you still have 6 protons, but if you count up the neutrons, now you'll see there are 7 of them, giving you a total combined mass of 13. And we have carbon 14, which still consists of 6 protons in the nucleus, but now we have 8 neutrons in the nucleus. These are the 4 flavors of carbon, or the 4 isotopes of carbon. They're the same element, but their masses are different. Here you can see all the isotopes together. They look adorable. Okay. Now, how do you find the most common isotope? Well, the most reliable way to do it is to actually look it up on an isotope chart. You can actually find these. I've got a copy of the CRC Handbook of Chemistry and Physics, and there's a whole section in there that lists every single isotope of every single element and includes things like what is the mass, what is the relative abundance, and if it's radioactive, how does it undergo radioactive decay, what's its half-life. You could look this up on the internet also, but a really simple, quick way to do it, it doesn't always work, but it works most of the time, is to just take the atomic mass that you see on the periodic table and round it to the nearest whole number. Now, again, it doesn't work all the time, but for the purposes of this course, it will work fine. So carbon 12 would be the most common isotope for carbon, and carbon 59 would be the most common isotope of nickel, and oxygen 16 would be the most common isotope of oxygen. So how exactly did they calculate these weight average masses? Well, I'm so glad you asked that question. It was so full of foresight. Oh, amazing. Anyway, what you do is use this incredibly complicated looking equation, but really all it means is that you're going to have multiple isotopes, and if you know what their percent abundance in nature is, you just basically say, well, if 30% of it, if the 30% of the atoms are isotope 1 and 70% of the isotopes are isotope 2, you take 30% of isotope 1's mass and 70% of isotope 2's mass and add them together. Okay, still confusing? All right, so let me show you the example here. What is the weight average atomic mass for chlorine if it has these 2 isotopes? So we have chlorine 35, which makes up 75.53% of all atoms of chlorine, and chlorine 37 makes up 24.47% of all atoms of chlorine in the universe that are naturally occurring. So what we do is we set it up. Because chlorine 35 makes up 75.53% of all isotopes, we take 75.53% of 35. Notice I'm doing this by using the decimal, multiplying it through. And since chlorine 37 makes up 24.47% of all isotopes, we're going to take 24.47% of 37. And then we're going to take those two numbers and add them together. And you'll notice that the weighted average mass, 35.489, I always tell my classes just round it to the nearest thousandths rather than worrying about sig figs for this. But you'll notice that the weighted average mass is closer to 35 than it is to 37. You would expect that. If you round it off to the nearest whole number, you get 35, which is the mass of the more common isotope. And that's how they get the weight average masses you see on your periodic table. You take whatever percent of isotope 1's mass there is and whatever percent of isotope 2's mass there is. And if there's any additional isotopes, you just keep going and then you add them all together and that gives you the weighted average mass. It's actually very, very simple. And go ahead and try some because the more you do, the better at it you'll get. That is all you need to know about the particles in the nucleus, also known as nucleons. And until next time, ladies and gentlemen, I bid you adieu. And as I always say,